Hello, today we're going to talk about the use of program complexes ANSYS and PLAXIS 3D in assessing the influence of the density of sand base on the modulus of deformation. Annotation and introduction. The results of comparison of calculated and experimental values of the modulus of deformation at different densities of the sand base are presented. The simulation was carried out using the software package ANSYS for the viscoplastic model plus MISO and PLAXIS 3D for the elastic plastic Mohr-Coulomb model. The article presents the results of comparing the values of modulus of deformation determined by the Schleicher formula based on laboratory studies and the results obtained by modeling using ANSYS and PLAXIS 3D. Basic materials and methods. The tests were carried out in a metal tray with rigid sidewalls measuring 17 cm, 55 cm, and 53 cm. The base microfine sand homogeneous. In experiments, the density of the base was changed 1.66, 1.62, 1.59, 1.53, and 1.48 grams on cubic centimeter. The internal friction angle for sand was determined at a density of 1.62 grams on cubic centimeter and was 59 degrees. The sand base was formed layer by layer compaction using a metal rammer to achieve a given density. The thickness of each layer was 5 cm. During the test, the settlement was determined over the entire load range by the H10. How is a How-type indicator mounted on the reference frame. A hard metal plate with a diameter of 120 millimeters was used as a foundation model. The load on the plate was transmitted using a lever system with a gear ratio of 1:10. The loading stages were assumed to be equal to 0.1 of the ultimate load. Each stage was maintained until conditional stabilization of the settlement, 20 minutes. Loading was carried out either before failure, at which the settlement increased without increasing the load, or until the conditional maximum settlement of the foundation was obtained. Modeling technique and basis analysis tools. Numerical simulation of the experiments was performed using the software package ANSYS and PLAXIS 3D. The development of displacements was limited in the X and Y directions. The displacements could only develop in the vertical directions, that X is equal to 0 and Y is equal to 0. Two models were used to model the base. First is Mohr-Coulomb Model, and second is a three-dimensional finite element model of plus MISO, multilinear isotropic hardening. Mohr-Coulomb Model. The simplest known condition is a strain condition formulated in 1773 by Charles Augustin de Coulomb, using the Mohr method, which can be presented as first formula, from which it can be seen that the value of the intermediate main stress sigma 2 does not affect the strain of the soil. Using the strain condition, the theory of the ultimate stress state of a loose cohesive medium base and its application to solving a number of engineering problems has been developed. In the stress invariance and the strain condition can be represented as 2. In the principal stress space, the Mohr-Coulomb condition represents an irregular hexagonal pyramid, as shown in figure first. This condition is widely applied in practice mainly because of the simplicity and acceptable accuracy in solving specific engineering problems. On figure first, you can see Coulomb-Mohr strain condition. A is in the space of main stresses, and B in the plane of main stresses. To obtain numerical solutions using a finite element model of the Mohr-Coulomb material, in the 10 noded elements in PLAXIS were used in modeling the soil matrix. The modulus of deformations used in the program was calculated using the Schleicher formula based on experimental data. The Poisson ratio V is 0.3. The plate model had dimensions D is equal to 120 millimeters. Thickness is 10 millimeters. Elastic modulus you can see, and the plate was modeler using a linear isotropic model. A three-dimensional finite element model of class MISO multilinear isotropic hardening. The MISO material model is used to model linear and non-linear soil behavior. The non-linear behavior of the soil is modeler using a multi-line model of isotropic hardening MISO material. This model includes the von Mises Weil criterion. When estimating the stress-strain state for sand using the plus model MISO in the ANSYS program, the first point of the stress-strain state curve must be the yield stress. Subsequent points determine the elastic-plastic response of the material. The equivalent stress equation has the form for where S is the deviator stress, sigma E is the current yield stress, sigma K is a function that depends on the plasticity of the material. For the case of isotropic hardening, sigma K can be determined from an actual strain-stress curve. When using PLAS, MISO by ANSYS solid 186 for soil modeling and solid 187 for the linear isotropic plate model were used as an element type. All other source data is the same as in the first model. Results. Tables 1, 2, 3 and figure 2, 3, 4, 5, 6, 7, 8, 9 show the experimental values and results obtained by ANSYS using the viscoplastic plus model MISO and the Mohr-Coulomb elastic plastic model for PLAXIS 3D. The values of the modulus of deformation were determined using the Schleicher formula. 5. The values of the modulus of deformations were determined using the Schleicher formula, where is a coefficient taken for round plate of 0.8. D is the diameter of the plate. V is a Poisson's coefficient taken 0.3%. Delta P is an increment of the average pressure on the plate foundation on a plot of the linear relationship between pressure and settlement. Delta is a settlement increment of the plate when the pressure changes by delta P. On this slide you can see table 1, table 2 and table 3. On table 1 you can see dependence of sand base modulus of deformation E on the pressure at a density of 1.48 grams on cubic centimeter. On table 2 you can see dependence of the modulus of deformations on the density of the sand base under ultimate load. And on the table 3 you can see dependence of the modulus of deformation on the density of the sand base at P is equal 0.03 MPa. On this slide you can see figure 2, figure 3, figure 4 and figure 5. On figure 2, you can see dependence at a density 1.48 grams on cubic centimeter. Figure 3, you can see dependence at a density 1.53 grams on cubic centimeter. Figure 4 is dependence at a density 1.59 grams on cubic centimeter. And figure 5, you can see dependence at a density 1.62 grams on cubic centimeter. On this slide, you can see figure 6 and figure 7. On figure 6, you can see dependence of the plate settlement of the pressure at a density 1.66 grams on cubic centimeters. On figure 7, you can see 3 diagrams is a dependence of the plate settlement on the pressure at a density of A density 1.62 grams on cubic centimeter. B is 1.59 grams on cubic centimeter, and C is 1.53 grams on cubic centimeter. And on this slide, you can see figure 8 is a dependence of the plate settlement on the pressure at density 1.48 grams on cubic centimeter. Conclusions. A change in density of base from 1.53 to 1.62 grams on cubic centimeter resulted in 1.57 times and increasing the disruption load and changing density of base from 1.62 to 1.66 grams on cubic centimeter to 0.42 times. Values of the modulus of deformation increased by 1.43 in 4.5 times, respectively. In comparison with the experimental results, the closest calculated values were obtained using the PLAXIS 3D model at the initial loading stages and during failure. Thank you for your attention.